All right, I wanted to come back in and add in a little mini topic back into 6.7. I thought that it was not going to be on there because I thought this was part of Unit 8, but I realize now that this is part of Unit 6. So we do need to kind of talk about this, and I want to just go back just to make sure that I'm thorough just in case it shows up on an FRQ. So the first part we already talked about. I'm just kind of doing a little bit of review to kind of remind you of this part, which is if you've identified or defined an accumulation function as the integral from 3 to x, and remember that the starting value down here is kind of just helps you determine what a constant would be in terms of the antiderivative. So we're going to find a simplified, expanded version of f of x by evaluating the definite integral. So just to remind you how that works, like this is what I would call the quote-unquote long way to do this. And our job is to understand the shortcut, but we're going to do this a long way the first time. So the first thing I would do is calculate an antiderivative of the derivative t squared plus t plus 1 dt. So that antiderivative would be 1/3 t cubed plus t squared, 1/2 t squared plus t, and then instead of putting plus the constant right there, we're going to evaluate this from 3 to x. Then remember that what we do to calculate the definite integral is we take this general antiderivative and we go ahead and we plug in x and we plug in 3. We calculate the net change. Let's say notation-wise, just so that we can kind of talk about this, let's call this the derivative little f prime of t. All right? And then let's call this antiderivative, okay, which is, remember, this is just one of the many antiderivatives. Let's call this f of t. And now watch, when we go to plug in our net change, then we're going to calculate f of x minus f of 3 over here. And so I plug in my values for x. So I'm going to have 1/3 x cubed plus 1/2 x squared plus x. And then we plug in 3. All right, and I'll leave the arithmetic to you, but it does end up being 16.5 when you calculate that net change by plugging in 3. And so you see that this actual lower bound, just somebody had asked me that before, changing this lower bound will change the constant. It's kind of like an initial condition of where you started from for this accumulation function, capital F of x. All right, so we've determined what capital F of x is. And notice that kind of as we're looking at the relationship between these, that the little f of t was an antiderivative. And I was using the antiderivative where c was equal to 0. And then we calculated our net change. And notice that what we got over here, capital F of x, the accumulation function starting from the value 3, is going to be exactly another antiderivative, but it's an antiderivative with the constant equal to 16.5, and this came from basically using the starting condition or initial condition, starting condition that if I were to calculate f of 3, you would get 0 on that. And you can check that out and kind of see what we have going there. And I just realized I do have a mistake right here. This should be a minus because it's minus f of 3 there. All right, so that's kind of this idea. And why is f of 3 equal to 0? That's because if I was doing the integral from 3 to 3 of t squared plus t plus 1 dt, that when you start at 3 and end at 3, how much area have you accumulated? The answer is none. So that's like your initial starting condition is kind of hidden in there by that beginning value that's there. Now, what they've asked you to do here is once we have found this accumulation function, capital F of x, which is starting from this initial condition of 3, they want you to go ahead and take the derivative. So f prime of x over here with our, it's going to be the derivative with respect to x of 1/3 x cubed plus 1/2 x squared plus x minus 16.5. And the derivative of 1/3 x cubed is going to be x squared plus x plus 1, right? Just using our derivative. And hopefully what you are noticing and what the shortcut that we talked about before is that what's inside of here is the derivative, okay? So remember that kind of as we were looking at this, that was f prime of t. That was the derivative, okay? And so when we are doing what's inside of here, this is the derivative of actually both this generic antiderivative I did over here where c was equal to 0, but it's also the derivative of the accumulation function over here because the constant doesn't matter. So this derivative inside of here, notice that there's a change in variable though. The inside had t, the placeholder variable. Your final function, because of the x here, should have x in it. So this is f prime of x. And so all we did, our shortcut for fundamental theorem of calculus says the derivative of the antiderivative is simply what's on the inside. And the only thing is the input variable needs to be changed to match your input variable. So that was the beginning part of this, that the derivative of the antiderivative or the derivative of the accumulation function is simply going to be whatever is inside of the definite integral with the correct variable placed in it. Okay? All right, so that's the first part of this, kind of recapping where we were. All right, now we're going to come to part 2, a special case. All right, so this is really very, very straightforward. It's simply, so this is just recapping what we just did in the example above, that if the accumulation function is defined with a definite integral, and we don't really care where this starts, this beginning value will set the c constant in our problem. Okay, we basically know that f of a is going to equal 0 is going to be your initial condition. Right? And then when we take a look at this, and you would plug that point in and use that to find c. Or you could simply just do the net change, right? The net change, which would be to calculate an antiderivative, usually the one with the constant equal to 0, and calculate the net change by plugging in x and plugging in a and subtracting them. But instead of doing all of that work, what we're going to see is that you don't have to. If they ask for the derivative of an antiderivative, provided that when you look at this, so this is what we're going to, our target, our shortcut, provided the number here is a constant, and the number up here, the top bound, is going to be the variable x. It has to be an x there. Then we simply just take this input, plug it into the derivative inside, and that becomes the derivative. Super easy when you look at it. So here, evaluate the derivative of 1 to x. Notice that I have a constant in x, so I meet that requirement. And then I want to take the derivative. The answer is going to be secant of x. And we're done. Here, same thing. I check constant and x. And so we want to take the derivative. So this is going to be equal to the square root of x cubed sine of x, and we're done. And notice that the placeholder variable inside is a moot point. It doesn't even matter. It can be any letter that we want it to be. Over here, notice your variable, placeholder variable is k. Again, it doesn't matter. Notice we check. We have a constant. We have x on the top. We meet the requirement for the derivative of the antiderivative. So this would simply become e to the x square root of x plus x squared over ln of x, and we're done. And it doesn't really matter, just as a reminder, it makes no difference what constant is here, because what that constant does is it sets the plus c part, like it actually finds the plus c part, but when I take the derivative, that part always goes out because the derivative of that c is going to be 0, so we can kind of ignore what the starting value is. Provided that this is a constant, that's all that matters when we look at it. All right, so now we're going to extend this into a chain rule problem. All right, so now we're going to look at the chain rule and see how this applies. All right, now notice that the change, which is how I'm going to know I need chain rule, is that this is not a constant and this is not x. So the minute you see either of those, it doesn't have to be both, but either one, we know that we are going to use chain rule on this. Now I'm going to show you the why of how we use chain rule, and then we're going to basically do this as a shortcut. So when we're doing this problem, your first thing that you would do is take this derivative and find an antiderivative. Let's call it capital F of t. And we're going to evaluate that from the low bound h of x to the high bound of g of x. But don't forget, what we're actually doing is taking the derivative of that. I'm just working on the inside. All right, now continuing this on, we would be taking the derivative with respect to x of that antiderivative with g of x plugged in, minus the derivative of the antiderivative with h of x plugged in. And when I show you this step right here, hopefully this is going to be like, oh, now I see why this is a chain rule problem. So now I'm going to go to take the derivative. I'm just going to put it down here. You would have the derivative of the outside function times g of, or with the stuff inside, times the derivative of the inside minus the derivative of the outside function with the stuff times the derivative of the stuff. And remember that the derivative of the antiderivative is simply what's inside of here. Remember, recall, f prime of t, whatever, is equal to f of t, little f of t. So this becomes little f, but you plug in g of x times the derivative of g of x minus little f with h of x plugged in times h prime of x. So it ends up being a chain rule problem. All right, here's how I would approach each of these problems below. All right, we don't want to do the long way, which is actually finding the antiderivative that we're going to use. For each of these, I want you to think of it in a kind of a loose fashion and say what we're trying to do is to take the derivative of an antiderivative with the top bound plugged in minus an antiderivative with the bottom bound plugged in. Once you have that, now you're going to go, I'm going to take the derivative. The derivative of this would be f prime 2x cubed times 6x squared minus 0, because f of 1 is a constant. And then you want to think about what is the derivative of the antiderivative. That would be this function in here. So we simply use that function, and it becomes secant squared of 2x cubed times 6x squared, and that's the derivative of the antiderivative. All right, let's look at the next one. Same thing. The derivative with respect to x of some antiderivative with 7 plugged in minus some antiderivative with e to the x plugged in. So this becomes f, well, actually 0 for the first one. Sorry, I'm trying to rush here. 0 minus f prime of e to the x times e to the x. And remember, f prime is the function inside of there, so we plug and chug, and it becomes e to the x squared plus 5e to the x, and that whole thing has a negative in front, and times e to the x, and then that would be our derivative. All right, one more at the bottom here. Why don't you try it and then come back and check your answer. All right, so coming down and taking a look at what I've done so that you can check your answer. I did a generic antiderivative, I used chain rule, right? Chain rule over here for each of these portions. And then I plugged in the function that we started with, which was the quote-unquote derivative.